Okay, so today's lecture will be about pneumatic control valves. Control valves are used as control elements to manipulate flow rate. So on the right is our diagram of a control valve, and you can see this valve part, and then there's also this chamber up here that we show as well. And in practice, a control valve looks like on the left. This is one type of control valve, and we have flow coming in here and it exits here. And then this stem here, this is called a valve stem, and it can be pulled up or down to open or close the valve. And in this chamber up here, it's sandwiched between a diaphragm, which is a membrane, and the air can push on the diaphragm. It can either push it up or push it down, and that opens or closes the valve by pulling up or pulling down on this valve stem, respectively. So we'll talk a bit more about that later. So pneumatic control valves are actuated by a signal consisting of gas pressure. So this gas could be either air, which is the cheapest option, or nitrogen, which is a more expensive option. The reason that you might want to use nitrogen is when you're in an environment where you have a volatile organic compound that is explosive and you don't want to introduce oxygen into the environment. So now we have the pneumatic signal, P, that is fed to this chamber, and I use these cross hatches to indicate that it's a pneumatic signal. The industry standard pneumatic signal ranges from 3 to 15 psi. You might wonder, why not 0 to 15 psi? The reason is that we need to distinguish between air loss and a low signal output from your controller. So now if someone comes in with an axe, chops your air line in half, and you lose air, you can distinguish that from your controller outputting the minimal value. So it's really for troubleshooting. There are two types of valves that you can order if you look online. Some valves you can configure to be either. That's air to open or air to close. An air to open valve, the more air you have, the higher the air signal, the more open the valve becomes. So an air to open valve at 3 psi is fully closed, and then as you add more air, it becomes more open. At 15 psi, it's fully open. I.e., as we increase the P, the pneumatic signal, F increases in an air to open valve. Air to open valves are also called fail-close valves because if you lose air, then by default, the valve will remain closed. On the other hand, an air to close valve, the more air you have, the more closed it will become. So at 3 psi, the valve is fully open. At 15 psi, the valve is fully closed. I.e., as you increase the pressure, P, your pneumatic signal on the valve, F will decrease in an air to close control valve. Air to close control valves are also called fail open valves because if you lose air, then the valve will be open by default. So it depends on, so you might wonder, which one do you order then for your process? And the answer depends on the situation. It's usually comes down to a safety consideration. So let's consider a situation where there's a leak in the airline and we lose air pressure. So now the pneumatic signal goes to 0. Let's consider two situations. In one situation, you have a control valve for cooling water to a nuclear reactor. And what we need to do is think about what happens when you lose air. What we want is the valve to fail such that we maintain cooling water flow to the nuclear reactor to avoid a meltdown. So we want this valve to be fail open, i.e. air to close. You need air to close it. So so this way, for safety, if you lose air, it remains open. So if we go back here, let's see. Air to close, fail open. So the other situation we'll consider is when this control valve is for a toxic, highly reactive feed into a reactor. So now what we want is for, if we lose air, we don't want that toxic and highly reactive feed spewing into the reactor by default. Instead, we want the valve to fail close, so that when we lose air pressure, that valve will by default be closed and avoid spewing unwanted toxic and highly reactive feed into the reactor. I.e., we want this valve to need air in order to be open. So these are two scenarios that you can consider to gain insights into which one you would choose for your process. So now let's go into a bit more detail about how one of these valves might work. So how fundamentally can we arrange a valve to be air to open versus air to close? So one way that some valves work, you have a valve stem, right? And remember, it can be pushed up or pushed down. And the more you push it down, the more this flow coming through this pipe will be restricted. The more you pull it up, the less that flow will be restricted and F will increase, right? So if you pull the valve stem up, F increases, push the valve stem down, you decrease F. So an air to open valve works as follows. So this valve stem here is right here, and it's attached to a diaphragm, so a membrane. And then there's a spring that pushes down on the diaphragm. And in an air to open valve, you feed the air signal down here in the bottom. And if you increase the air pressure, it's going to push up against that spring, push this valve stem up, and it's going to allow more flow through the pipe and open the pipe more so that you have more flow. So that's how it works. And if you consider when this air signal goes to zero, you lose air, what happens is the spring will win the force balance, push down this valve stem, and the valve will be closed. And so that's why it's a fail-close valve. On the other hand, let's look at the air-to-close valve. The only difference is the air signal is now fed into the top of this chamber, and it pushes down on the diaphragm as P increases. So it's still pushing against these two springs. So if you increase the pressure of air, it's going to push down this diaphragm, pushes down the valve stem, which restricts the flow. And so the more air you have, the more closed that valve will be. And again, if you consider when the air signal goes to zero, what's going to happen is this spring is going to win the force balance, push this valve stem up, and the valve will be open when it fails. So it fails open. So this should give you a bit of insight into how these can work. So now for my last slide, it's very important to know whether or not your valve is fail open or fail close in order to choose the correct sign, i.e. plus or minus, of the feedback controller gain. So we haven't seen P control yet, but this will be their first introduction to a proportional control law. That's where the P stands for, comes from. So let's say that F is our controlled variable, this flow right here. And let's let FSP be the set point for the flow rate F. And in order to maintain the set point, what we'll do is adjust this, okay? So this is going to be your controlled variable. This is going to be controlled. And this is your manipulated variable. So the feedback control law will specify the manipulated variable in terms of the control variable. And indeed, this is your first P control law. So you specify the pressure P as P bar, it's an offset, plus a term that's proportional to the error. And the error is the difference between the set point and the actual flow rate, okay? And this Kc is up to our choosing, its magnitude and sign, and it's called the controller gain. So this is a setting of your controller, of your P controller. And if you'll note, when the error is zero, i.e. when F is equal to F set point, and we're at business as usual, the pneumatic air signal P is equal to P bar, right? So this P bar is the pressure that's required to maintain F at its set point at steady state conditions, at business as usual, okay? And if there's an error, you need to adjust the pressure that goes on here. And it's automatically done by this control law. All right, so to see why it's important to know if your valve is air to open or air to close, let's suppose that your flow rate is less than the set point, okay? So the set point is greater. So what this implies then is that your error here is positive, right? Your error is positive. And what it also implies is, well, I'll say and. What we want now, since the flow rate is too small, we want the valve to open. In order to increase the flow and bring F up to its set point, right? Because F is too low. And now consider when you have an air to close valve. Well, if you have an air to close valve, the more air you put on it, the more it will become closed. So what we actually want is to put less air on it in order to open it. So what we want P to go down, right? We want the pressure to go down. And in order for the pressure to go down for an air to close valve, what we want to happen is for Kc to, well, not what we want to happen, what we want to do is set Kc to be less than 0. That way, when the error is positive, P will decrease. On the other hand, for an air to open valve, it's the opposite situation is true. So we'll go through it again. For an air to open valve, the more air you have, the more it will be open. So we actually want more air for an air to open a valve, and you want P to increase. And if you want P to increase when the error is positive, that means you need to set Kc to be greater than 0. Okay? So it's very imperative to know whether or not your control valve is air to open and air to close, and to go through this logic with the signs. Otherwise, the controller will act in a completely opposite direction as what you intend.